Hello everyone, this is Dr. Singh and uh, I am going to discuss the rest of the lecture on UV visible IR and please bear with me. There are some slides not correctly and they are also please refer to regular PowerPoint on Blackboard, and as you can see some of them already covered in the lecture last time, and we were here last time when we discussed about the absorptivity. Um, we were talking about the how certain molecules can absorb more light and some of the other molecules absorb less light, so you may need different concentration to bring to the same level of absorbance when you are running these the methods you are using. Also pH, ionic strength, solvent, some other characteristics which should be fixed while we are conducting experiments, so we can compare basically apples to apples, because these factors will affect the absorption of light by these molecules. So if your pH is different, then the molecule will absorb different amount of light, so that will not be directly proportional to the concentration. It is now depending upon the pH, so you have to fix the pH so you can compare how much concentration is present. So these things need to be considered while we are running the test. This is giving an example of certain spectrums you can see when you are running UV visible spectroscopy. This gives you an example of chlorophylls. There are chlorophyll A and B as indicated here. Certain groups are present in chlorophyll A and B, and if you go back to food chem, we talked about some hydrolysis which can happen while we are processing or we are storing chlorophyll containing foods. And as you can see, the dotted line here has different peaks, whereas the bold line on this one has different peaks. So actually, in fact, we can distinguish chlorophyll A and B while we are if we want to determine if chlorophyll A or B they are interconverting or something is happening to chlorophyll while we are processing. So if you choose this wavelength and the peak is going high, it means chlorophyll A is being produced or reduced during depending upon what is happening, and same thing with chlorophyll B. So suppose is if this peak is going down, this peak is going up while you are processing, you check all the samples, it means that chlorophyll A is being degraded and B is produced while we are, and that will change the shade of green color into your food product. Same thing, you can see carotenoids, they also have their own specific spectrum, and you can see they are overlapping too, so you have to be very careful which wavelength to choose to detect these molecules. So but this is how these spectrums they look like. This axis is nanometers, the wavelength, whereas this axis is the absorption. And there are various ways they have studied these systems, and this is an example of photosynthesis rate, you know, as we determined with the wavelength. So although this is not for us to understand right now here, but the main thing is various molecules they have various peaks which can be used to determine their concentration. Another way which sometimes the formula is written is epsilon value, when the concentration of absorptivity is into centimeters inverse and mole inverse, then the same A value which we saw before can be written as epsilon value, which is molar absorptivity, and that's mainly which is used to compare apples to apples. So how many moles for per mole, what is the epsilon value of that particular molecule. So if you have 1 mole of solution, some molecules will absorb more light when there is one molarity as compared to other molecules. So epsilon value is actually is used to uh, to compare that. So correspondingly, the concentration of the solution should be represented in molarity, not in percentage or anything else. So if you are determining or you are measuring absorbance using absolute value, then we should be using concentration and molarity. Those are some of the things we need to be careful. So, okay, so this slide is upside down, so please bear with me. And but just I'm going to discuss a few things which we discussed before also, but this shows you how various things can happen when incident light is shining through the solution, absorbing solution, and how it can change, while it's coming back out. So it can be absorbed by the solution, or it can be scattered. If the particles are there or some other things are there, it can be scattered. But in addition, you can see this cell can also reflect some of the light during this process. That's why we zero the blank or zero with the empty cuvette, so we can take care of this part, so we can have the reading which is really due to the absorbance of light by the solution. Um, and also, as we discussed before, the formula for absorbance is log of transmittance, which is equal to P naught over P, and it shows you how um, the solvents sometimes also absorb something or reflect something, so sometimes we zero with the solvent also. So this is simply just showing you that part. um, Continuing further, so Beer's law is used, but there are problems with the Beer law. It has its own limitations, and one of the limitation is that you cannot use very concentrated solution. You have to use dilute solutions because molecules. This is a sensitive technique. Molecules are involved in determining the light absorption. So, if you have more and more concentration, you have more problems you may have in that. So it's you need a dilute solution. You cannot just take a concentrated solution and just put it in the cuvette and find out how much concentration is. You saw that in our Biot method or Lorry's method, that we had to bring it to that concentration of micrograms or milligrams per ml of for the particular protein solution. It's true for all the other solutions, for vitamins, for metals, for any other reaction you are going to determine. These techniques are really sensitive to concentration, so you have to have dilute solution. Because what happens is when you increase the concentration, there are intermolecular means that two molecules may come across close to each other when you increase the concentration, and they may affect the charge distribution, and also hence the absorbance of the light in a molecule. So that is another thing which can happen, and you have to be careful with that. um, it's a little bit detailed, but if you see the peak, sometimes the peaks are broad, and that's called as bandwidth. And it is, it is depending upon what kind of molecule again it is. So it can how close the electronic vibrational levels are, so it will give you a broader. Sometimes the peaks are sharp, and that's easy to determine. Then you pick up that particular wavelength. But when there is a broader peak, then that could be a problem. So you have to know what we are going to do. So just be careful with that. Be needing this in your regular use in labs in industry. There are various kinds of cuvettes available. The one we are using in our lab, they are mostly made up of polymers or plastic, and they are disposable. Um, they are most suitable for water-based or aqueous solutions, and also they are in the visible range, not in the UV range, because the sample hold or the cuvette will absorb light in the UV range also. So if you need to use UV range, then you need to use quartz or fused silica, and that they are really expensive for that part, and that's why we don't see them very often unless you're doing research or you have some specific need to observe things in the UV range. Mostly we do. That's why we do. But it's much cheaper to do in a colorimeter, a spectrophotometer with the UV only or visible only. Sorry. So that's what. And also I told you that the path length is fixed for 1 centimeter, and that's what we use in all our calculation. It basically makes it simpler. You just substitute 1 in the path length parameter, and that is simple calculations otherwise. We plotted the calibration curve. I think I don't have to discuss too much about this. As you increase the concentration, your absorbance will increase, and this will give you a straight line with the R square value mostly should be around 0.9 or more. So that's what we used for correlations. And then if you know the unknowns absorbance, then you can drop a line on the standard curve, and then you can see how much concentration it has. So that's what with that. Again, this is an upside down slide, but it gives you the normal schematic for the UV absorbance equipment, and you can see it's pretty simple if you know the basics. So you need a source for radiation. You need UV or visible light, a lamp. In UV visible spectrophotometer there are two lamps, and you can hear them changing while you are conducting the experiment, and you change the wavelength. And then there will be a wavelength isolator. Basically it is a grating, or it can be a filter which filters particular wavelength of light. So if you fix at 540 nanometer for biunit, it will just let 540 nanometer light pass through it, and the rest will be blocked. And if you are using for Laurie's method 750, it will let only 750 nanometer light pass through, and the rest will be blocked, and so on. So then the light passes through the sample holder, and there are photoelectric detector which will compare the light coming from originally coming from the radiation source with the coming out after coming from the cell or the cuvette, and then it compares and give you the readout device, like you have a screen, and then of course you need power supply for that. So this is a simple schematic for that one, and this shows you how various wavelengths are filtered through. So there is a source here which reflects the light, and then it focuses light at various wavelengths are separated and they are focused, and there is a filter or grating which lets only one wavelength, in this case only lambda 2 is, which may be 540 nanometers or 750 nanometers. So it moves to let lambda 3 go out, or let the lambda 1 go out, or lambda 2 go out. So these are all the wavelengths possible, and they are just filtered to various microns. Okay, so continue again. I'm sorry about the upside down slide here again. This indicates that I think we have discussed this before also. Most of the UV visible, these absorbance are linked to the electronic transitions. It means that the double bonds, like the pi bonds, are mostly absorbing this light, and they are jumping onto next electronic level, and that's what the UV visible spectroscopy is. So normally UV radiation is around 200 nanometer. Mostly we are looking at the non-bonded electrons, and we are looking at the unsaturated double bonds which we were talking about before, and they contribute to the absorbance of light. So if you have no nitrogen, oxygen, double bond, C double bond carbon or anything else, you may not see the absorbance. And this is the table I showed you before for the lambda epsilon value, which shows you the absorptivity. But you can see most of the molecules, they absorb in visible light, especially when they have conjugated double bonds. The other ones, they might absorb in the UV light because they don't have uh, conjugated double bonds. So you need more than one double bond or two double bonds conjugated to go into the visible range. Otherwise, you will see mostly they are being absorbed below 300, and that is UV light mostly. So, but that they are also used to detect. So, non-conjugated systems, you can see they are all below 300. Conjugated systems, as you go along, some of them they are above 300 coming up, but again, if you don't have enough conjugation also because of the benzene and all that, they also don't, they are colorless, they don't show colors. Are only when you have a lot of double bonds and a bigger molecule like anthocyanins, carotenoids, and many other dyes which we use in our Biuret method and all that. They are of course salts, copper salt and all that, so they are colored. So anything with color we can see can be done with the visible light. Otherwise, most of the organic molecules are colorless and they need you. The other part I discussed a little bit is the fluorescence spectroscopy. I told you that the antioxidant capacity ORAC determination is by fluorescence, and there are other uh, methods which require fluorescence spectroscopy to be used. It's very similar to UV, and as I discussed with you, I'll discuss it again here a little bit. That it is similar to UV spectrophotometer, but it's very sensitive. It's more sensitive um, than the UV spectrophotometry, and that's one of the reason why it is used. And many molecules they don't show UV, but then when you excite them, they show fluorescence spectroscopy when the electron drops down to lower level. So signal when you have the you are determining the emission, not the absorbance in this case. So the electrons are excited to higher energy level, and then they drop it down and they show so the process is activation and deactivation. So first the molecules, the electrons go up, and then when they drop down they emit the light, and the emission is being recorded. This is how it works. So when you shine light, it will absorb, and then slowly the thermal deactivation happens. These are rotational levels or vibrational levels. So molecules, they don't stay on the top, and they want to dissipate their energy as heat to the solution. And then once they reach here, they drop down to lower levels, and then emission is, I told you that emission is in every direction. It's not in the path of light, so it can be everywhere. So fluorescence light can be emitted in all directions, and that's measured. This emission spectroscopy, so it's measured there. Sometime as I discussed about the phosphorescence, I don't know if you remember that there are singlet and triplet states. When two electrons are paired, it's a singlet state, and when they are unpaired, that is a triplet state. So sometimes these transmissions happen, and triplet states are more stable. So that's where, if it stays like that, it can keep the light, hold the light for a longer time, and phosphorus shows this light being emitted at night, and that's what is called as phosphorescence, which I told you before. So there are fluorescence and phosphorescence, two kind of uh, processes which can happen in the emission spectroscopy. So that's what we are determining here. They're more sensitive and can be determined, uh, help to determine the concentration of the solution. Um, Again, shows you the how we are determining it. Just to clarify more, same thing as UV spectrophotometer, radiation source, wavelength isolator. The incident light is shined on the sample. This side was your UV visible spectroscopy, whereas because this is absorption, how much light is absorbed, whereas the emission will happen in all direction. When the molecule is emitting light, it doesn't distinguish between this direction or that direction, it just emits light in all direction. So mostly the observation is done on the right angle of the incident light. So that's where the detectors are, and that can be, red, and you can, of course, power supply is there. So absorption spectroscopy, emission spectroscopy, and this is UV visible spectroscopy. This is your fluorescence or phosphorescence if you are using that. F stands for fluorescence here. So this is what is happening here. And again, we have a relationship of phosphorescence, the light being emitted in this case is PF, and then it is related to the concentration. So it's same thing, but the formula is a little bit different. But it's basically it's showing you that it's a concentration related to the concentration, and you can plot standard curves, and you can use the same technique you use for the UV spectrophotometer, and you can apply it over here. But the concentrations are really low. That's why it's very sensitive technique. Be careful when you are plotting this. And this shows you the same graph, and as you increase the concentration, the fluorescence intensity increases, but you can see it's varying here because of the molecular interactions. So you have to be careful. The same thing, it's just repetition of what happens during UV spectrophotometer. So I told you that this is very sensitive again, and there can be a linear relationship, but you have to be careful how long the linear relationship lasts, and you should be in that range. And I think this is just a write-up of what the diagrams we saw for the instrumentation, that it has radiation source, wavelength selector, sample holding, radiation detector, readout. So it's something. Sometimes the slides are, I say something on the other slide where the pictures are, and then there's a write-up for that. So just read those things in the book. Again, it's exactly same what happens with the UV spectrophotometer solutions. Same parameters are applicable: temperature, solvent, impurities, pH. All these things may affect the environment of the molecule, and hence the absorbance, and the reading of the fluorescence. Okay, we are going to move a little bit into now a different picture of IR. As we discussed, there were vibrational levels. If you go back to the energy level diagram, electronic states, vibrational states, and rotational states. I asked you that question in the quiz also. So there are various ways that, as I told you, that vibrations can happen. A water molecule, simply in this case, can vibrate this way. It's called a scissoring. It's like a scissor. This here, and then it can asymmetric stretch, that it is going this way and the other one going out. Symmetrical stretches, it's going both ways, and this is going this way. So, and this is going this way. So there are various kind of stretches or vibrational modes which can have, and as I told you, that some of the techniques, they use different kind of symbols for units for wavelength, and in this case it's called as wave number. So when you the spectrum of the IR, which I will show you in the next slide, it lies in it is shown in a different way than normal spectrum, which we talk about in UV or visible spectroscopy. So IR radiations are electromagnetic radiation with longer than visible but shorter than microwave. So they are in between visible and microwaves. Longer means they are less energy, so the wavelength is higher, energy is less, and the wavelength lies between 0.8 to 100 micrometers, and you can divide that into near IR, mid IR, and far IR. So that's how the units are written here, but near and mid IR are the most commonly used in there. So the normally radiation is measured in frequency, not in wavelengths, as I will show you in the diagram here, that it is inverse of the wavelength. So, and we call it as wave number. So remember this thing, that it is centimeter inverse because it is reciprocal of wavelength. So the term wave number is used instead of nanometers, or directly as a length unit. It is inverse of the length. So that's the wave number, how many waves are there in 1 centimeter, basically. That's what it is. And you can see the frequencies, they are represented as 3000 or 1200. And you can see, so this technique gives us that what kind of vibrations are possible, and once we know which vibration absorb which kind of wavelength, then we can distinguish if that particular group or bond is present in the molecule or the mixture you have or not. So if there is an absorbance of light at 3100, we can think that there will be double bonds, alkenes are present. If we see a stretch of CO at 1735, it means aldehydes are present. If we see OH at 3600, which is very very common in water containing or sugars, then we can see this peak. So it's kind of a fingerprinting where you can see that, okay, if this peak is present, then this kind of structure we can expect. And that's the whole thing about spectroscopy. But it's not single technique is not enough to distinguish it, but multiple techniques, when put together and they show same information, then you can conclude that some kind of groups are present in that. This is how it looks like. It's upside down slide. So the peaks are reverse. Percentage transmittance is being recorded and wave numbers are used. So it's very different from UV. It looks very different. But say this is the part where H2O or OH groups will be shown up. So you can look at the table. Each peak is because of some vibration of the molecule. So if you know that this peak belongs to CO, or this peak belongs to something CH stretch, or this belongs to H2O, so you can write down which kind of stretches or which kind of vibrations you see in this spectrum, and then you can go to another uh, technique and see NMR or IR. IR is this one, NMR or UV or mass spec, whatever, and then you can say you can compare that, and then you can conclude from multiple techniques whether something is present or not. So it shows a sharp band at 1700 or so, which is around here, shows you that there is a carbonyl group. So this is how we determine that which groups are present or not. So this is a neat technique, but it gives you some of the molecules present in there. And NIR is very very common in food industry for quantitative analysis. As I discussed before, that commercial instruments are available, which they have been kind of standardized and made for determination of proteins or certain other molecules. Moisture, you just slide in very non-destructive technique. Of course, it's not a primary technique, but it's a secondary technique which can be which has been standardized by these companies to. So what happens is that you shine the light, the NIR. If I know that, okay, this food product has 10% moisture or 20% moisture, I slide it and reflect, the light reflects in certain way, and certain bonds, if water is present, will be absorbing IR radiation because of the vibrational, those vibrational transitions. And the detector is now standardized to determine that fingerprint. So it is fed into the microchip that if these kinds of reflections are coming, then water is present, or if this is so high, then 10% is present. If it is that high, more high, then it is 20% moisture. So that's how you standardize it, and then these instruments are very quick and industry in various ways to determine the protein content directly or moisture content directly. um, I will skip this one. We normally do not use these kind of techniques. They're a little bit in depth, so I will skip this one for the city. What we need to do just shows you that um, NIR is used in various ways, and um, in chemical and pharmaceutical industries they use a lot this technique, and now it has been used in food applications for determining the wheat variety actually. So we can detect that identification of orange juice samples from the sources, authentication of source of olive oil. So you can go very deep into that, and it's a kind of fingerprint. Every kind of molecule or a food product has its own fingerprint, and if you know the fingerprint of your control, then you can compare and say if olive oil from California has a different fingerprint as compared to from Spain or from Europe. So you can compare those two oils and maybe even distinguish how much oil, if there is a contamination present in there. So these techniques are really powerful and they are very quick. uh, Protein moisture oil in cereal oil seed is also determined. It's also used in uh, to inspect those things in US and Canada. So NIR is a good technique and buy these equipments, and now they are very standardized. And again, it's continuation of the same thing, that you can evaluate the composition of red meats, and you can do dairy products, non-dairy spreads, moisture determination in butter and margarine, moisture fat determination in cheese, lactose protein moisture in milk and whey powder, and sugar, total sugars, soluble solids in. So you can see how good this technique is, that it's very non-destructive as well as quick, but it's not again a primary technique. It has to be standardized. You need to have a control to know you are measuring accuracy, you determining the accurate thing, because these are not standard. When you evaporate moisture in oven, you know its moisture is, until you have, or unless you have the volatile compounds, but you know that their moisture is evaporated at 100 degrees Celsius. But this machine weighs the moisture, but you have to calibrate it with the standard method, and you need to know that how much moisture is present initially to calibrate this machine. So there are few things which you need to be careful, but nowadays um, absorption and reflection of light of various frequencies has been used. So NIR is non-destructive. It measures the vibrations of the interacts with the vibration of the molecules, and on that basis we have designed these molecules to detect all these different components of food in the mixture of food. That's the good thing about it. So that is it, I think I have. So uh, I will check again where we are with our lectures, and communicate with you, and on the announcements, please follow the announcements. I'll be back. I'll see you guys on Monday then in the lab. Okay, thank you very much. Bye bye.